Now, if we had known this, Giovanni is not listening, but you should. Had we known in 1999 that it would be almost impossible to retire this job, would we have done it or not? I'm sure we would have some done. Okay. So I would like to explain why, once you have set up an impact monitor system, it is morally impossible to stop doing it, unless you can capture somebody else who takes the responsibility. You can find somebody else which is stupid enough to accept to replace you with these commitments. Now, the problem is the following. In principle, when we discover an asteroid, the orbit is very poorly determined, then we have a lot of problems with non-linearity, low probability impacts, and so on. As the object is reobserved, the orbit becomes more and more accurate as a result of the fact that the possibility of impact is posted on the web. Astronomers are pushed to observe it, and then if things go well, the object is reobserved until when the probability goes to either 0 or 1. Let me mention the trivial theorem. The probability of impact in reality is either 0 or 1. It's our level of information does not allow to discriminate the two. So as our amount of information grows, the probability will either go to 0 or go to 1. Okay? Well, sometimes it does strange things in between, goes and goes down. But in the end, it must go either to 0 or to 1. It goes to 1, then some space agency has to mount a deflection mission. Maybe somebody else will speak of these kind of things in this meeting or somewhere else. On the contrary, in most cases, what happens, if the orbit is well determined, then the confidence region, even projected on a target plane in the next, any target plane in the next 100 years, becomes small. And the probability that actually hits the Earth is small. The probability that when the Earth is at a point which corresponds to minimum distance, the asteroid is actually there, if the region where the asteroid can be is very small, is small. So practically speaking, the asteroid, as the orbit is well determined, is unlikely to be near where the close encounter can occur. And by the way, if there was a VI, it would be possible to compute it by using the linear probability theory. So if you have an asteroid which has observed a multiple apparition, or even more, a numbered asteroids, essentially they do not appear in the output of our impact monitoring system. However, the condition of having a very small distance between two orbits can last for long times. It's something which is in the end erased by secular perturbation, but can very well last 50, 100, even in some cases 200 or 300 years. So what happens if you have an orbit which is very well determined, but then, because there are multiple opportunities of a close approach, there is actually a very close approach, not an impact, but a very close approach. Then this close approach can result in a large scattering. So I would like to use one particular example for this. And this example, I would say the most important example on which most of our developments of this theory is based is the asteroid 99420. Sorry, there are 3 nines here. 99,942 Apophis. This asteroid is going to have a very deep encounter with the Earth on 13 April 2029 at a distance from the center of the Earth of 38,000 kilometers. That is lower than the geosynchronous satellites. Then, as a result, if you draw the confidence region, I can explain. The runoff is the longest axis of the confidence ellipsoid in space. It's essentially in the direction of the motion. As a result of the close approach, this long axis, that is the worst direction from the point of view of our knowledge of the orbit, is increased almost instantaneously by a factor more than 4,000. In few years, the propagation increases this value to 40,000 times, the value before 2029. As a result, if you try to compute the counter image of the Earth on the target plane of 2029, the counter image of the Earth, instead of having a diameter of 12,000 kilometers, has a diameter of 12,000 kilometers divided by 40,000. Counter image of Earth is a very narrow curved strip, and the width of this strip is 600 meters. In other words, now we know the orbit of Apophis almost perfectly for all practical purposes. In particular, there is no risk whatsoever that there is an impact in 2029. The Earth is missed by 30,000 kilometers, and the uncertainty is a small fraction of this distance. It's actually a few kilometers. But after that encounter, an impact in 2036 or 2037 could occur, and to be able to exclude this impact, we need to compute the orbit of Apophis to an accuracy of a few hundred meters. In other words, the concept that an orbit is good enough to avoid impact risk, is a temporary concept. Before the encounter it is enough, after encounter it is not. If you take into account that after 2029 the asteroid can have other encounters, this results in an exponential increase with time. That is, the orbit is effectively chaotic. If you compute the runoff at the year 2150, the length of this confidence ellipse, of course in the linear approximation, is 100 AU. That actually means that the ellipse is not an ellipse because it wraps around the orbit dozens of times. You have an uncertainty that corresponds to much more than one revolution around the sun of the asteroid. Essentially, after 2029, an asteroid which is numbered is very good orbit, has also been observed with radar as an extremely accurate orbit, is I would say, it's like somebody who was at university sent back to primary school. Is demoted to the level of the newly discovered asteroid. As an orbit, it becomes uncertain as well of the one of an asteroid which is discovered since 1 week. The state of being an asteroid with good orbit is a temporary condition for an air. For a main-belt asteroid, the point will be completely different. Therefore, impact modeling must start again. Even if we are sure that nothing is going to happen now, until 2029, after that time, we have to do it again. Of course, a very close approach like this is very rare. I'd like to point out for your amusement that no asteroid is visible by eye. Not even Ceres, the largest one, which is magnitude 8 at best. In 13 of April 2029, Apophis is going to be visible by naked eye. And this is the only event in history in which an asteroid will be visible. This gives you an idea how rare is this event. There have been a lot of rumor about the asteroid 2014 RC, because it was passing very close to the Earth, but the maximum magnitude was something like 11. That usually needs a reasonably good telescope to see it. In this case, it's naked eye. It's a very unlikely event. However, all asteroids in the M-wave, all the near-Earth asteroids in the M-wave like that. So this is another example which is called 2009 FD. Giovanni Vassecchi will speak about this again, but I am only interested in showing this. This is again is the runoff. That is the longest asteroid position on Saturn. This is a logarithmic scale. So at the time of discovery, time now, the period in which it has been observed, the accuracy is a few kilometers. The accuracy of the order is a few kilometers. After a sequence of encounters, it becomes 1 million kilometers. Then, in 2185, you have this love trace, which is millions of kilometers long, and this love trace actually includes the possible impact. That means there are also very close passage to the Earth, and this results in a behavior which is similar to the one of Apophis, that is a very large increase of the uncertainty by a factor for the nominal about 1,000. And then after that, who knows? Anything can happen. From this figure, if you were to compute a formal Lyapunov time of this interval, you would get a Lyapunov time of 14 years. However, as we don't, in the theory, the people who compute Lyapunov indicators threshold with this, Lyapunov indicator is a temporary value. In the case of near-Earth asteroid, the Lyapunov time you would estimate by taking account of the time interval during which the distance of the two orbits of the asteroid of the Earth is small is much shorter than the real Lyapunov time. You know why? Because the minimum distance between the two orbits is not small anymore after the year 2200. So from here on, you don't have another possibility of encounter with Earth for another 4,000 years. That means the way these asteroids really behave from the point of view of chaos, they have a short period of time in which they accumulate a lot of divergence, and then they have a regular orbit for thousands of years. Then we have again a few hundred years of chaos, and so on. And in the end, this level of divergence, which is a factor 300,000, has to be deleted not over 100 and how many is this? 176 years, but over 4,000 years. So the real Lyapunov time is not 14 years, but is 30 times more. It's more like 400 and 500 years. Well, in case you are interested, Christian Marshall has written, conjectured that in reality the n-body problem, all the Lyapunov exponents really computed to time plus infinity actually are zero. This is a conjecture nobody has been able to prove, but not to disprove it either. So it's not clear that positive Lyapunov exponent actually exist in the n-body problem. We don't have any formal proof of their existence apart from, of course, periodic orbits. For a generic orbit, which is not periodic, we don't know that they exist. Okay, but this maybe is too much mathematics. So that means how can I explain this? As an example, it's normally stated, in particular by NASA, that all the near-Earth asteroids, which are larger than 1 kilometer, 90% have already been discovered. Let's suppose the remaining 10% discovered something which probably will happen in the next 20 or so years. After all of these have a well-determined orbit, let's suppose they all are numbered, is the work of impact monitoring finished? No. It's finished until the next close approach. It scatters the orbit in such a way that we have to start from scratch. Okay? So
you cannot retire in 2018. Never ends.
It never ends. Never ends. In other words, let's suppose NASA and very soon we hope Pisa start up a system of telescopes which are the purpose of monitoring near-Earth asteroids. In principle, the goal is stated as discovering these objects. Fine. After they have been discovered, can you turn off the telescopes? The answer is no. You have to continue for an infinite time. The Earth must be protected, not only from the asteroids which are not known, but also from those you already know and which have already been declared to be safe. But please remember, the declaration that they are safe is for a short time. There's a finite time span. At the moment, we are not even trying, at least not in the operational system, to compute possible impacts for a time span longer than 100 years. What happens if we try to do a computation for longer time? There are several things which can be done. This is a little bit of a technicality. If you have a scattering encounter, you can define a LOV which is adapted to the scattering encounter. In a way, this solves the problem which I have mentioned, which is actually the coordinate system that should be used to compute a LOV. There is an optimal metric to compute a LOV. This optimal metric is obtained by using the metric on the scattering plane. But this is only a small portion of the problem. The other portion of the problem is the Yarkovsky effect. Now, what is the problem? Even if you are able to determine, as an example for Apophis, the semi-major axis of Apophis at the level of few meters, nevertheless, this is an instantaneous value. And the secular perturbation of the semi-major axis, which I produced the Yarkovsky effect as described by Menios yesterday, introduce an uncertainty which, over long enough time, can be very important. How much important? This is a very simple order of magnitude computation. This is the value. I'm using a value which is not exactly the same used by Menios, but the same order. Let's suppose we have a d over dt of 10 minus 9 astronomical units per year. Let's suppose that semi-major axis is 2 AU. This is an long track acceleration, and then we can compute that the quadratic acceleration in longitude has a long track effect. So I multiply the change in longitude, in mean longitude, by semi-major axis to have a dimensional quantity which corresponds to the runoff, and it's given by this simple formula. You take the number of revolution computed in radians times the amount of change of semi-major axis. So if I have 10 to minus 9 AU per year in 30 years, and I've done 10 revolutions, then I get a displacement by 10 to minus 6 for the magnitude astronomical units. And this is a small fraction of the Earth radius. So it looks like this is not important. Even after 100 years, the effect is only 1/3 of the radius of the Earth. Then, moreover, this is a variation along the LOV, so it cannot really create or destroy a VR. Then why is this important? Well, this is important because, let's take the example of Apophis. The displacement of Apophis by 2029 is very small. But very small with respect to what? With respect to the distance from the Earth, that's 1,000 kilometers, yes. And with respect to the 600 meters, which is the size of the target Earth, there's another keyhole, another very small portion of the target plane that leads to an impact in 2068, which has a width of 2 meters. So to conclude that the impact is going to happen in 2068 or not, we should, as a matter of principle, compute the orbits of Apophis until 2029 with an accuracy of 2 meters. With respect to that, the Yarkovsky effect is enormous. Why is this? because the small effect of Yarkovsky, which is much less than 1 radius per Earth, when it gets multiplied by 40,000, or by one very close approach, or by a very large number as a result of the sequence of close approaches, as in the example of 2009 FD, is going to produce a difference between being very close to the Earth or being impacting the Earth. It is the combination of the non-gravitational perturbation with this quadratic accumulation in time, with the amplification exponential in time due to chaos, which makes the very small effect of non-gravitational perturbation makes the difference between impacting and non-impacting. Now, what are we supposed to do? We are supposed to make a model, a dynamical model, which includes the Yarkovsky effect. But then we have to estimate the Yarkovsky effect. How we do that? There are essentially two ways. One way is that you define some empirical parameter, which is, roughly speaking, an acceleration which is transversal, that is perpendicular to the radial velocity, which is constant or maybe a function of radius. And this you add as a parameter. This is, if you remember in my first lecture, this is one of these mu. It's a dynamical parameter which has to be added of the list of parameters. So instead of determining just 6 initial conditions, you determine 6 initial conditions plus 1 Yarkovsky parameter. Then you have a 7 by 7 normal and covariance matrix, and then this 7 by 7 matrix you have to treat like a 6 by 6 one. The other possibility is to make a physical model, and this can be done because the Yarkovsky effect is a thermal effect. So you can actually compute a solution to the heat equation for a given rate of insulation, which depends upon the spin axis of the asteroid, the rotation rate, the thermal inertia of the surface of the asteroid, and many other parameters. And then you can following methods which have been established by Farinella, Petrucci, and others a long time ago.
Probably also need shape model.
Again, at one level you do for a spherical model, and then if you have to do it more accurate, you have to take into account the shape, which can make a lot of difference.
5 meters.
Sorry?
If you're looking for a few meters.
For a few meters, you certainly need to take into account very fine details of the shape of the asteroid, possible variation of the thermal constant, depending on which parts are covered by regolith, which parts are solid rock. I mean, it's, again, it's an infinite work. Okay. Now, as for approach 1, we currently have a list of 21 asteroids with a Yarkovsky effect which has been measured by actually doing a 7-parameter orbit determination with a signal to noise in the Yarkovsky effect at least 3. Another 13 which are, well, marginal, and this is a paper published last year. For approach 2, the problem is that, unfortunately, the number of asteroids for which we have enough information is more or less 0. The only asteroids for which we have all the information are the ones which have been visited by space mission. Or we will have them for asteroids which will be visited by space mission like Osiris. Marco Polo, unfortunately, is not going to happen. And therefore, if you use the approach 2, trying to make a model, a physical model, in the end you have use a statistical model, which takes into account the uncertainty of all the quantities which appear in the formulas in the semi-analytic solution. So this is an example of this approach applied to the asteroid Apophis, which were mentioned before. Now, this is a model of the Yarkovsky effect. Now, please note that this is a 0, and there is a negative. It's clear that there is a bimodal distribution. This bimodal distribution looks like the superposition of two Gaussians. The Gaussians are obtained by some error modeling, the measurement of the strange quantities like the thermal conductivity of the surface. And the bimodality arises from the fact that the Yarkovsky effect is, in particular the diurnal Yarkovsky effect, is positive if the spin axis is up. That is the rotation of the asteroid is in the same sense as the orbital rotation. If you want, the angular momentum of the rotation is in the same direction as the angular momentum of the orbit, and is negative in the other case. And now, if you ask why this is higher, we don't know the rotation axis of Apophis, so in principle we have two hypotheses. However, this hypothesis is more likely than the other. You know why? It's very simple. This has to do with what Manius was discussing the other day. Nea have to come here from the main belt. To come here from the main belt is easier if the Yarkovsky effect decreases the semi-major axis than if the Yarkovsky effect increases the semi-major axis. Because if it increases the semi-major axis, the asteroid goes in the arms of Jupiter, which provides to eject from its solar system, and the probability of coming near the Earth becomes much less. If the asteroid comes down at some point in the encounters, as an example, the Nu-6 resonance or the 3-to-1 resonance, and is sent to us. So this is some representation on the information a priori we have taken account of everything, the models, measurements, even population models, and theories of transport of asteroids from the main belt to here. This, on the contrary, is the information we have from observation, and you surely will note that this is a Gaussian. And it is a Gaussian because, of course, the only source of uncertainty here is the error model, and the error model in the observation we are using as a Gaussian. So this is just an example of what I've shown to you, and this is a very linear case, of course. Therefore, we can combine these two probabilities by the appropriate Bayesian approach, which essentially says that you have to multiply them. And therefore, you get a combined distribution taking into account both the astrometry of Apophis, all the other observations, all the other models. Then you propagate this to the target plane of 2029. This is one of the two coordinates. This is zeta, one of the two coordinates on the target plane of 2029. And then on this target plane, we show one vertical bar for each keyhole, that is, for each point which would lead to a collision in a later year. So as an example, you see here 2068. On the contrary, 2036 is here. 2036 is really unlikely. It's almost at the Z0 false state. Not possible in reality. But 2068 is still there. Even if the width of the keyhole is just 2 meters, nevertheless, you have a non-negligible probability because unfortunately this is right in the place where there is a maximum of probability density for the Yarkovsky effect. And another very important point, look at the red curve is what the probability would be if you were to completely neglect Yarkovsky. And it is very important to show that if you use the wrong model, the result is completely wrong. Because if you make the assumption that there is no non-gravitational perturbation, and then solve for the orbit, you have, of course, only 6 parameters. And what you are doing is, I'm sorry to insist in my preaching, you are using a conditional rather than marginal uncertainty. That is, you are the red curve is the uncertainty conditional to the fact that the Yarkovsky effect is 0. What you should use is the marginal probability, which takes into account of the uncertainty introduced by all parameters. Okay? So it would be like this. Then in particular, the 2068 impact would be impossible. So for getting the Yarkovsky effect, the results are completely wrong. In the sense they declare something impossible, something which actually is possible. Now, this is it is clear that this is a case which is beyond the capability of our automatic impact monitoring system because of this extremely strong chaotic effect due to the close approach in 2029. So this is something we do hand by hand. Let's say we publish a paper for each case. I have to say that the editor of Icarus at some point was a little skeptical on this idea of publishing one paper for each case. So, the last paper was sent to another journal. But still, we are still in the stage in which each new case, when you try to do this kind of extreme impact monitoring, we are still in the learning phase in which each new example requires some new idea. There is no way to automatize this at all. Anyway, at this point we are close because this, I'm showing you two impact monitoring computation. One of these two is used in Pisa. This one, using the Off-LOV method. And the other one, with this used no a priori model for Yarkovsky, only astrometric information. The other one use a priori Yarkovsky model. They use two different JPL ephemerides, and this is a Monte Carlo. And if you look at the results, of course, the glass is half empty or half full. What you get is that the probabilities are the same within a factor of 2. So these are two computations which are as different as we can do it. We have used completely different and inconsistent methods in the two computations. And the result now is a difference by factor 2 in the estimation probability essential. Well, we think not. The reason we think not is that anyway, we don't need to take a decision on what to do with this possibility of impact now. We can delay the decision after the year 2029. There is no need to deflect now. It's not necessary to deflect before 2029 because it has been computed that it is possible with technology with perfectly known of deflection to operate even in the year 2040s. So we don't need to decide immediately whether an impact is possible or not. This is another example, which is based more or less on the same principle. This is an object which is more than 1 kilometer diameter and has a probability of impact in 2880, which is 4 10 to the minus 4. This is a rather interesting case. This has not yet been done. We have not yet done the equivalent of what is done with Apostle, trying to use two completely different methods to compare and measure the reliability of the computation. Just let me, how much time I have? Mancano 15.
15 minuti, no, 5 minuti, sono 11, non ci devo finire.
Mancano 2 minuti. Vabbè. Insomma, decidete voi quanto mi date, 5 minuti, va bene, faccio 5 minuti, non preoccupate. Va bene. Ok, let me a few minutes just to show you our last example. The last example is the asteroid 101955 Bennu, which is interesting, especially for NASA, because it's also the target of the OSIRIS-REx mission. The value, this is the asteroid which is better observed. We have a secular acceleration, let's say the rate of change of semi-major axis is 1.9 10 to minus 9 AU. And 1.90. Now you may think this is daring to give 3 significant digits, but the signal to noise in this is 200. So the error is really 1 in this unit. So we have measured the Yarkovsky effect with precision 1 in 200. the transverse acceleration, which has an uncertainty which is in femtometers per second square. It is a strange unit. Could be considered one of the smallest microscopic forces which has ever been measured. This gives you an idea of how complicated it is to do this kind of business, because in this particular case, the relativistic corrections are extremely important, and we had to improve the relativistic model of the motion of this asteroid to obtain this result in such a way that it is reliable. And this is the figure corresponding to the previous one. This is a model PDF obtained by taking account of the possible uncertainty and the knowledge of the Yarkovsky effect. And these are all the possible impacts. Okay? The bars represent the keyholes, that is a possibility of return in the year which is indicated, and essentially the height of the bar times the value of the probability density at that point gives the probability of impact. And this is an example of risk value computed for an object in the 22nd century, actually toward the end of the next century. And this one and 2009 FD, which has been done recently, are the only two cases in which we have been able to do a real impact monitoring with almost 200 years of advance. The cumulative impact probability is 1 in 25,000, and this has been just published. So, let me draw the conclusion, which is positive and negative. This is an endless job. That is, we must continue to take care of new discoveries of new asteroids, even if they are small, because even they would make a small damage, but still the damage can be serious locally. We have to follow up the old cases forever, pushing forward the time horizon. We have to monitor the adequacy of the dynamical model and upgrade when necessary. I have given already the example of non-gravitational perturbation and relativistic correction. We have to solve for the Yarkovsky effect whenever possible, and even if we are not determining the Yarkovsky effect, we have to take it into account in uncertainty. And also we have to be ready for immediate impactors, which are discovered and impacted in a very short time. So, unfortunately, we have found an interesting job when we invented these methods about 15 years ago, but we have not considered sufficiently the fact that this is a job from which it is essentially impossible to retire. Nevertheless, I hope to succeed. This would really be my greatest discovery in retiring, but this requires that somebody else, which is not a strict research institution, like the ones which were involved in the work of 15 years ago, takes responsibility for this action. Now, this is the subject of the visit of this afternoon, because this is, at the moment, appears to be succeeding. That is, we appear to have convinced the European Space Agency to take over the responsibility of managing this system. And you will visit this afternoon the place where a center, which is called the Neo-Coordination Center, is being built. And this is being built to take over the responsibility of this computation. This does not mean we'll stop assisting ESA in this work, but they will take responsibility for the handling of the operational system. If this succeeds, this is a great relief. On the other hand, the American system, although it is operated by Steve Chesler, the same person who did the original work with us in 1999, is operated under responsibility of NASA. Is space agency, JPL is not a pure research institution, it's a space agency, it's a branch of the space agency. And therefore, in this way, the two systems will be more parallel institutions than they are now. And I think this is the correct solution. Nevertheless, we have to make sure that this transition is smooth, and particularly that the difficult thing is that the quality of the work done by Pisa must be at least equal to the one of the work which was done in university and research institution, and this is not trivial, or maybe it's possible very expensive. Of course, much more expensive than in the university environment. And this is the price which I think has to be paid. Thank you. Non ci fare sorpresa, ho fatto tutto vedere tutte le mie trasparenze, mancare tutto.
Claudio, one question about the 2029 flyby by office.
Yes.
Surely there will be gravitational scattering and making things worse in terms of knowing its orbit. At the same time, it will be probably observable, it will be by radar. Will that not compensate the accuracy, the available accuracy?
To be honest, I don't think the observation during the flyby will constrain so much, but the observation done immediately after the flyby will constrain the orbit to a level which is, roughly speaking, 40,000 times better. That is, of course, we will know the orbit of Apophis after the close approach much better than we can predict it now. As a result, what will happen? The probability density will shrink enormously. Okay, so look at this probability density here. There are several possible impacts inside. It became probably as flat as the red line. And after that, most impacts will be excluded. If one remains inside, it will be very light. Okay? This is the rule of the game. But the improvement, I expect that in 1 year after the encounter will be an improvement in the orbit quality factor. I don't know, maybe 10,000 or something like that.
John? But actually, it's not a question. I would like to add to what Andrea said, that if after the 2029 encounter, Apophis were found to have passed through the keyhole, that leads to the 2068 encounter, we will know that very exactly. But unfortunately, we have also very little leverage to use to deflect the asteroid, because before the 2068 collision, there is only a very shallow encounter in 2051. And since the encounter is shallow, the multiplicative effect of the deflection done before the passage from the day is very small.
Do you think it's not enough, the 2051?
I don't know. Therefore, we can make the computation. But it's not so promising as to deflect, as it was to deflect away from the.
Well, on the other hand, to do the deflection before 2029, I think it's impossible, because we never have enough knowledge at the level of few meters before.
This is a safeguard for our jobs.
Just a short question, because I really don't know. In the model, the dynamical model that you used for very close approach, how accurate is the model for the geopotential, or how much does it matter?
We include, at the moment, we include the second order harmonics.
Do you think it will
Maybe we'll need more. After the fact, after the passage, we probably will have to use even higher order harmonics. But this, to be frank, is quite easy. Also because you are not introducing unknown quantities. The model is unknown. Currently, we must use the J2, otherwise it doesn't work. So, I think.
Because again, that it's the 2 meters or 10 meters that you're speaking about can be quite tricky.
Oh, it's not mentioned here, but we are using it.
Okay, thank you again.